Hi everybody, welcome to the fifth video here in this series on R. This is the second take because the first one, there was no audio, which I didn't learn until after, which is a bummer. So let me just quadruple check that I'm getting audio here. Okay, cool. So the last video was we took a break from R and I gave you like a visual, intuitive introduction to regression. And this video is going to kind of work through with the same data, the slides from the last video, but I'm going to kind of show you how to run some of your own regressions in R. So let's just do a quick rerun here recap about what regression is. So if you remember, we were looking at, in this last slide, this last presentation, we were looking at the relationship between median county income and support for Trump in the 2016 election. And we were thinking like, okay, a way to think about this, two things we might want to know from this are, oh my gosh, sorry. Are first, how, given some level of income, what's the average support that Trump got in the county? So average support conditional on income. And then also we're interested in how that conditional average changes, right? So as income increases or decreases, how can we expect on average support for Trump to increase or decrease alongside those changes in income, right? And remember, we're not talking about anything causal here. This is just correlational. So, we saw that like, okay, this is like a rough way to start thinking about like conditional averages, but like we don't have a lot of like, we can just kind of do this forever. It's kind of ad hoc. So let's put the constraint on it here that we want to draw this line through our data. And it's going to be a linear relationship. So it's going to be a single line through this data. And we're going to say that this data, or this line, is the line of best fit. It's the line that minimizes the sum of squared residuals, where the residuals are these green lines. So what this blue line does is this blue line is the line that if you take all of these residuals, so all of these distances between the blue line and each of these data points, and you put them end on end and you measured that length, there's no other blue line that you could draw through these data to get a set of those green lines that's any shorter. This is the line that minimizes the distance of those green lines set end to end. And so mathematically, how you would say that is it minimizes the sum of squared residuals. Remember, residuals, the green line here, the distance between our predicted value and our actual data. It's the sum because we're adding all these lines end on end. And then the squared part is just because mathematically, this is technically a negative residual, and this one's a positive one. And you don't want them to like cancel each other out, so we're going to square them all so they're all positive. So but that's really just to make the math. Okay, so that was regression, right? Now, what we're going to do today is figure out how we can calculate ourselves like the crucial pieces of information contained in this blue line. In particular, what we might be interested in is the slope of this line and how confident we are in the slope of this line. So the slope of this line is minus 0.0000252, which means that on average, if a county's median income increases by $1,000, then we should see a decrease in support for Trump of 0.0000252 percentage points. Now, obviously, that doesn't that's a very small number, and that's because our unit here is just $1. So, and as we're going to do in the R examples today, we're going to multiply by 10,000, and then we get a number that makes a little bit more sense. So on average, as a county's median income increases by $10,000, support for Trump in the county decreases by 2.5 percentage points. And this minus 2.52 is the slope of this blue line. Okay, so let's go to R. So in the folder, there is now another data set alongside that Mississippi data that contains the data that I used to make all those plots in the last presentation. So let's just see what it looks like. So you'll see that there's 3,114 rows for each county. We have median income in tens of thousands of dollars. Candidate votes is the number of votes that Donald Trump received in 2016. Total votes is the total number of people who voted in that county in 2016. Vote share is this, candidate votes divided by total votes times 100. And share white is the share of the county comprised of non-Hispanic whites times 100. And I believe this was from the 2015 American Community Survey Census data, ACS. Cool. So let's run our regression. So the key function here for running a regression is LM, linear model. And you'll see that if we look down here, the first argument to LM is the formula, and the second one is the data we're going to use. So let's see what our column names are here. So the general format here is, for the formula, is the dependent variable. Obviously, I'm just writing this out. This is not real R code. The dependent variable on the left-hand side, and then a tilde, and then the independent variables on the right-hand side. So the dependent variable in our case is the variable that we are interested in, the variable we're interested in predicting, the variable we're interested in seeing how it changes given another variable. So our dependent variable in this case is going to be the share of the county comprised of non-Hispanic whites, which is going to be share white. Our independent variable in this first case where we're just looking at, sorry. This is not share white. This is vote share. Share of our variable we are interested in explaining is the share of the county that voted for Donald Trump. Sorry. Independent variable. is the median county income. So that one is going to be median income. We are interested in explaining how vote share varies with median income. And then what data are both of these variables in? They are both in elections. Cool. So we run that and we get, you'll see that we get a couple pieces of information here. Specifically, we just get our two coefficients, and we see that our coefficient on median income is what we saw in those slides, minus 2.5. On average, as a county's income increases by $10,000, its share of support for Donald Trump decreases by 2.5 percentage points. Our intercept, if you remember slope-intercept form, M is going to be the coefficient on median income, so it's going to be minus 2.518. But in order to draw a line that doesn't go through the point 0, you need to have this intercept value that lets the line intersect different places along the y-axis. And so that's what B does. And so B in our case is 75.3. Sometimes your intercept has a substantive meaning, other times it doesn't. This one it doesn't, because this is saying that on average, a county with a median income of $0 has 75% of people in that county support Donald Trump. And since we don't have any counties with a median income that low, that doesn't really make a lot of sense. Even though it is feasible for a county to have a median income of $0. Okay. So that's fine, but really what we want to do is assign this to an object. I'm going to call it out_LM. This is going to contain a lot more information. So here I use the summary function to get a bit more information about our regression line. So now we still see our estimates, but now we're also getting some information about how confident we are in those estimates. So here are our standard errors. Standard errors are kind of a measure of like the dispersion of our estimate, and they're a necessary thing for calculating confidence intervals as well as p-values, which I talked about in the last set of slides. We also see our R-squareds, adjusted R-squareds, all that. Cool. So this is kind of capturing this information. But if you remember down here, we also did a little bit more of an interesting regression where we regressed support for Trump against both a county's income and the share of the county comprised of non-Hispanic whites. So this is saying holding fixed a county's median income, an increase in the share of the county comprised of non-Hispanic whites of 1 percentage point correlates with an increase in support for Trump of 0.5 percentage point, 0.562 percentage points. So as a county, holding fixed how much income people in that county make, as the county becomes whiter, it supports Donald Trump more. Likewise, we can also kind of flip that and say, okay, let's hold fixed the racial composition of a county. Let's hold fixed what percent of that county is white. And then let's increase county's income by $10,000. on average, holding constant racial composition, increasing a county's median income by $10,000 correlates with a decrease in support for Trump of 3.7 percentage points. Okay. We also have this constant down here. Again, doesn't really make a lot of sense in that this constant is saying if a county has 0 white people in it and a median income of $0, on average, it will support Trump 34% of the time. Or sorry, on average, the county will have 34% of the people in the county will support Trump. But we don't have any counties that look like that. Okay. How could we do that? So that's really easy. That's really easy to do. We're adding another explanatory variable. And so we can just pop that over right here on the right-hand side. We're not changing which variable we're interested in explaining. Just going to pop share white over on the right-hand side and run that. And now we get our estimates. These are going to be the same as here. And then our measures of confidence, which I talked more about. Okay. So I think the most important things with all of this are understanding what regression's doing, what regression's not doing, and what variables and data you need in what format in order to test the things you want to test. That's the most important part about this. And I kind of talked about a little bit last week. This is really just the nuts and bolts about how to do this in R. But I just want to say that there's a couple other things I want to show you about kind of presenting these findings, which maybe aren't the most important, but I think also have like a role to play when you're working with regressions. So I want to tell you about 2 packages, one of them for creating really nice regression tables, and one of them for plotting regression output visually. So the first one is called this Stargazer package. So you probably don't have this installed, so do install that package as Stargazer. I already have it installed. I'm not going to run that. So I'm just going to do library Stargazer. So Stargazer is a very powerful package, and it's also has one function in it, and that function is called Stargazer. And it's a very powerful function for making pretty regression tables. That's what I used to make this. So you can use Stargazer. And then let's do out_lm. And then just add type equals text down here and run that. So now you see that this hasn't changed anything. We were working with the same model. It's just presenting it in a nicer way. So now we see our results like this. This looks extremely similar to this. And it's in a great format. So there's different ways you can like get this. Well, actually, before I talk about getting it out, I should also note that you can put in different models next to one another. So let's add that first one we did. You can just add it right in. And now you'll see that we have, here's that first model we did where we're just regressing vote share on income. And here's the second one, we're regressing vote share on both income and race. So how can you get this out of R and into something to like to to into a paper or a presentation or whatever? Different routes. One of the, not the most reproducible, but a way that does work is you can just take this, copy it, and pop it into Word. The key is that you have to use a fixed width font, like, like Courier. C-O-E, Courier. And then decrease the size. There you go. So there's a regression table. So you can just copy and paste it. That's fine. I like to, so I use this word processing software called LaTeX, which I might talk about in a later video. And that's actually the default. And it looks like a bunch of nonsense. But basically what I do is I save all of this as a raw text file. And then this word processing software called LaTeX reads this in and just uses it to make a really nice looking table exactly like this. So that's another route too, but that's kind of outside the scope. Okay, so that's making regression tables. Next thing here is I want to show you how you can kind of present these results visually. So I think that oftentimes regression tables are tough to read and it's easy to zone out. I think that's especially true in presentations. I also think that's true in papers. I like to put the regression tables in an appendix and plot the results, because I think visually it's a lot clearer what's going on, and you can usually make your point in a lot more digestible manner. So what we're going to show now is how we could turn this regression output into a nice little plot that kind of tells you the same information, but just in a lot cleaner setup. And so what we're going to do is we're going to use this package called Broom, which again, you will likely have to install. I already have it, so I'm not going to do that. We're going to use Broom in conjunction with ggplot. What does Broom do? Let's take our data, the output of, let's use this one, the one that includes the race variable. And let's tidy it. This tidy function is in Broom. And let's run that and see what it looks like. I've assigned it to this clean_lm object. So check this out. So this has taken all of that information about the regression and summarized it into, crucially, a data frame. So rather than being in this kind of weird format that ggplot wouldn't know what to do with, Tidy has taken all of it and stuck it all into this really nice, clean data frame that we can now think about plotting. So this one contains, again, our estimate, our standard error, and then information about confidence, like these p-values. So what do we want to show? What I want to show is I'm not really interested in this intercept term. I'm interested in plotting our estimate of median income and share white, those two coefficients here, as well as a measure of how confident we are in those estimates. And I want to kind of plot those as points with bars around them indicating our confidence interval. So we're going to add this optional argument to tidy conf.int. And now we're going to have these confidence intervals. These are 95% confidence intervals. Excuse me. So if you remember the video last week, confidence intervals are kind of tricky to think about in a non-survey setting, which is why I kind of did it this resampling idea, which is technically called, the full term would be, or full name would be, a non-parametric bootstrap, but don't worry about that. But the idea here is, remember, I have all my counties in a big bag, put all my counties in a big bag, and I draw out I draw from the bag 3,114 times, the number of counties I have. So I draw out 3,114 times. But crucially, once I draw out a county, maybe it's Washtenaw County, I write down that I have Washtenaw County, and then I put Washtenaw County back in the bag. I'm sampling with replacement. So that means that if I did this 3,114 times, I might get Washtenaw County 5 times. Maybe I'm going to get Wayne County 0 times. Maybe I'll get some other county 10 times. Maybe I'll get another county 2 times. So as I do this, I do that for 3,114 times. And then I keep doing that whole process again and again and again. And specifically, imagine I did it 1,000 times. So 1,000 times I pulled out 3,114 counties with replacement. And then for each of those 1,000 times I did that, I calculated my estimate of my regression line. This is saying here that if I did that 1,000 times, on average, I would, or sorry, not on average, 950 of those 1,000 times, my estimate of the coefficient on median income would be between minus 4.09 and minus 3.38. Okay. Technically, that's not actually right, because technically these confidence intervals are calculated under some assumptions and not using the bootstrap method. But just we're talking intuition, we're talking conceptual here. Just think about it as that resampling method. I think that resampling method is just the better way to do it overall anyways. So and if we did do it with the resampling method, they would look extremely similar to these numbers. So that was just a brief tangent on that. Okay, so now we have this object with our confidence intervals. And so what we want to do is we want to plot these 2 rows. Okay, so we want to drop, I'm going to drop this intercept row. We're not very interested in it. So when we want to filter out a row, we're going to use filter. And I'm going to say term does not equal intercept. All right, so now I just have 2 rows. Okay, so now let's plot this. So this might be this is going to be a little bit different than the other ggplots we've done, because we have to use 2 geomes. So remember, the basic ggplot needs 3 things. It needs a data set. It needs variables in that data set. And it needs a geome that tells R how to visually map those variables in that data set. So I'm going to say the data is going to be clean_lm. And then this first geome is going to be the one we've used before, geome point. And I'm going to say X is equal to estimate, and y is equal to the term variable. So what's that going to look like? It's going to look like this. 2 points. Down on the bottom here, we have the coefficients. And on the vertical axis, we just have the two different variables. Okay? So this is giving us, this is plotting our estimates, but this isn't telling us anything about how confident we are in those estimates, right? So how are we going to do that? We're going to add on another geome on top of this geome that's going to contain information about our confidence intervals. So we're just going to add another plus sign, and we're going to do geome error bar, and we're going to do the horizontal version because we're kind of working horizontally. So what are the aesthetics that we need to provide to geome error bar H? And note, this is where this is getting different. We aren't providing the aesthetics inside ggplot. We're providing the aesthetics inside the respective geomes. Why are we doing that? We're doing that because the aesthetics, the necessary aesthetics, are going to be different across these two geomes. In particular, if we look at geome error bar H, the required aesthetics here are X-min, X-max, and Y. X-min is going to be our lower bound on our confidence interval. That's our upper bound. And then what's Y? Y is going to be term again. So now we've layered on this additional piece of information. We've layered on this information about our confidence in these estimates onto our plot, right? So this is another way of representing a regression table. Personally, I think this way makes a lot more sense. I would improve this plot a lot. Obviously, it needs a title. It needs better variable names. It needs different axis names, a bunch of stuff like that. I'd also, I think this looks like a TIE fighter from Star Wars. Like, I would trim these whiskers, all that stuff. More importantly, though, it also probably needs some sort of standardization of these two variables, so that we could maybe get a little bit more of a sense of, is share white or is median income, does that change more with support for Trump? And right now that's kind of tough because a percentage point increase in the share of non-Hispanic whites in a county is just like completely apples and oranges compared to an increase of $10,000 in the county's median income, right? Those are like not, like it's not even like they're the same type of fruit, like apples and oranges. Like those are just like completely different things. So we'd probably need to standardize these variables in some way, but that's outside the scope of this. So this is just to say this is another way to display regressions. If I was writing a paper on this, I would probably include a plot like this in the table and then put the full regression output, the table, in the appendix. So I'd have the plot in the table, or the plot in the paper, the table in the appendix. Okay, cool. I'm hoping the audio worked this time. Thank you very much, and I will see you next time.